Hi friends, in the last lesson I gave you a brief introduction or a general overview on what topology is and what it is all about. Now for those of you who have missed the first lecture, I provide the link to it in the description down below. Now in this lesson we will be going through a few definitions like the distance function or the metric space, open voids and open sets. So in the last class I mentioned something about the Euclidean space as being an example of a topological space, right? Now the Euclidean space is a type of a metric space which in turn is a type of a topological space, right? Now the topology or the structure of the Euclidean space is determined by something called the Euclidean metric or the Euclidean distance function. We will go into the properties of the Euclidean distance function or the Euclidean metric right now. So the properties of the Euclidean distance function, or the metric. Now, for any 3 points x, y and z in the Euclidean space, now note here that x, y and z are something which I use to label any 3 points in the Euclidean space, not as coordinates. X, y and z are not coordinates, but they are points. They are points in the Euclidean space. So for any 3 points x, y and z, for any 3 points x, y and z, like I said, these three are individual points. They are not coordinates. So don't confuse them with coordinates. So for any 3 points x, y and z in the Euclidean space, the Euclidean distance function, d of xy satisfies the following four properties. First one, d of xy is greater than or equal to 0 for any pair of points x and y, and d of xy equal to 0 if and only if x equals y. Okay. The second one is d of xy equal to d of yx for any pair of points x and y, or x and y. We know that, right? It's pretty intuitive. For any 2 points, the distance between x and y is the same as the distance between y and x, right? Now the third property is the much familiar triangle inequality, right? Which is d of xz plus d of zy is greater than or equal to d of xy for any 3 points x, y and z. Now there's a fourth property which distinguishes the Euclidean distance function from any other metric. Alright. Now that's what makes the Euclidean space unique among other metric spaces. Okay. So now that property is for any 2 points x and y. If you take any 2 points x and y in the Euclidean space, there exists a unique point M such that d of xm equals d of my equals half of d of xy. So what does this fourth property tell you? It tells you that for any 2 points x and y in the Euclidean space, right, you can find some point which lies in exactly half the distance between these 2 points, right? That's what this M stands for. The third point. The third point lies in between exactly half the distance between X and Y, right? And again, we could repeat the same process, right? We could again find another point between X and M, or even Y and M, which again lies at half the distance between either this or this, right? We can go on finding midpoints like these. So, and this midpointness property is what distinguishes the Euclidean space from all other metric spaces, right? So that's what makes the Euclidean space unique among all other metric spaces. Alright, so now we will pass on to our definition for the metric space. Alright. So, metric space. Definition goes like this. A metric space is a pair X comma D where X is an abstract set or a space, abstract set, and D is a function which is defined from X cross X to R. D is a function which is defined from X cross X to the real line, which is that is the distance. The function D is a real valued function which is defined on the set X cross X, right? Satisfying the following properties. What are they? The first three properties which I mentioned before. Which are they? D of xy greater than or equal to 0 for all x and y in X, and D of xy equal to 0 if and only if both x and y are one and the same point, right? If and only if D of xy equal to 0, D of xy equal to 0 if and only if x and y are one and the same point, x equals y, right? The second point is D of xy equals D of yx for any 2 points in X, right? The third point is the triangle inequality, the third property, which is D of xz plus D of zy greater than or equal to D of xy for any 3 points x, y and z in X. So if this function defined on x cross x satisfies these 3 properties, then the function D is called a pair xd where x is an abstract set in D satisfying. Then the function D, the real valued function D, is called metric on X, and X is called a metric space. Actually, is this pair XD. It is this pair XD which is called the metric space, but then we use it interchangeably with the set X itself to term it as metric space. Okay, so it's actually the pair XD which is called the metric space, but then we use it interchangeably to denote it as X as well. Alright. So we pass on to the definition of open balls. So open balls, open ball. Let x naught be any point in x and R be any positive real number, R be any positive real number, okay. Then the open ball with center x naught is a set let's set down here x naught, a set of all x element of x such that d of x comma x naught, the distance between the center x naught and any other point x in x should satisfy this d of x, this distance should be less than r. So the set of all points x which satisfies this inequality defines the open ball with center x naught and radius r. Okay. It is also denoted by, Br of x naught or even B of x naught comma r. Okay, so now we move on to the definition of open sets. Open set. Now, a subset A contained in X. Subset A contained in X is said to be open. Said to be an open set or said to be open simply if for every point x naught, in A, okay, there exists some open ball centered at x naught, which is completely contained in A, That is, there exists a positive real number r greater than 0 such that Br of x naught is contained in A. So subset A contained in X is said to be open if for every point in A there exists some open ball centered about it which is completely contained in A. Alright, then that set A is said to be open. That set subset A is said to be an open set. It's said to be open in X. I hope that's clear. Now I'll give you an illustration of, for open balls and open sets for better clarity. So let's pass on to that. Let's take a space X, right? I'm going to represent space X as a large rectangle, right? So this is a space X, and I'm going to take any arbitrary point x naught in the space X. So this is a point x naught, and we require a positive real number r, right? So let r greater than 0 be any positive real number, and I'm going to represent a length with this r. So I'm going to, okay, let's take this length to be r, and with this length I'm going to draw a circle. So There you go. So this trade is hard. Right? Now the definition for an open ball goes like this, right? The set of all x element of x such that d of x naught comma x is less than r, right? All those points of x which lies at a distance less than r, right? So that set includes all the points which lies in the interior of this ball, right? So I'll just draw it like this, I'll just shade it like this. But this set excludes the boundary, right? This boundary, it doesn't include the circumference. So this is how we represent an open ball, right? This is an abstract representation. We can't really draw an open ball for every topological space. For example, for high dimensional space, for 4-dimensional spaces, you can't, visualize. We can't draw an open ball, right? Now, so this, I think it's fairly clear. So this is an open ball, right? Next we should look into an open set, right? Illustration for an open set. So instead of point x naught, we take a subset A, right? A subset A contained in X. So I'm just going to draw some subset A. Subset A contained in X. Now this subset A contained in X is said to be open. Is said to be open if for every x naught in A, there exists some open ball centered at x naught, right? So it means that if we take any point x naught in A, right, some arbitrary point x naught in A, we could find some open ball which lies completely inside A. Okay, so that applies to any point which lies near to the boundary of A. Even there we can find a very small value of r, right? And then we can draw a small open ball there. So wherever in A, where in whatever point you are in A, you can find an open ball which is completely contained in A, then the set A is said to be an open set. Then A is said to be an open set. So I hope it's pretty clear now. So thanks for watching.